Right now, a spacecraft launched nearly 50 years ago is drifting through the coldest, most radiation-saturated environment ever directly sampled by human technology. It weighs less than a small car. Its nuclear power source is fading by roughly 4 watts every year. Its radio signal, by the time it crosses more than 15 billion miles of space and reaches Earth's receiving dishes, carries a power of roughly 110 billionths of a trillionth of a watt. And yet, that signal has carried back something no telescope, no theoretical model, and no computer simulation had ever been able to provide: the first direct measurements of the physical environment between the stars. What those measurements revealed is not what most people imagine when they picture the space beyond our solar system. It is not serene emptiness. It is not a peaceful void waiting to be traversed. It is an active, electromagnetically structured, continuously irradiated medium that poses challenges to any object entering it that go far beyond the obvious problem of distance. Understanding what Voyager found and what it means requires first understanding what Voyager left behind. Voyager 1 launched on September 5, 1977 from Launch Complex 41 at Cape Canaveral, Florida. A Titan IIIe Centaur rocket carried it through Earth's atmosphere and set it on a trajectory toward the outer solar system. Its twin spacecraft, Voyager 2, had launched 16 days earlier on August 20th, but on a slower trajectory designed to pass all 4 gas giants in sequence, a gravitational tour that had never been attempted before. Voyager 1 took a faster, more targeted path. It flew past Jupiter in March of 1979 and past Saturn in November of 1980. During those encounters, it returned scientific data that rewrote what we knew about the outer solar system. It revealed active volcanoes on Jupiter's moon Io, the first time volcanic activity had ever been observed on a world other than Earth. It photographed Jupiter's Great Red Spot in detail never previously captured. It studied Saturn's ring system and returned the first close observations of Titan, the moon with an atmosphere thicker than Earth's, a dense orange haze of nitrogen and hydrocarbon chemistry. After the Saturn encounter, Voyager 1's planetary mission was effectively over. The gravitational slingshot from Saturn had flung it upward out of the plane of the planets at roughly 38,000 miles per hour. There was no target ahead, no planet to photograph, no moon to investigate. But there was also nothing to stop it. Newton's laws require no fuel to maintain velocity in the absence of friction. Voyager 1 simply continued outward, second by second, mile by mile, year after year. Voyager 2 followed a longer route. It visited Jupiter, Saturn, Uranus, and Neptune, completing the only grand tour of all 4 outer planets ever accomplished. Its encounter with Neptune in August of 1989 remains the only close-up study of that planet in history. After Neptune, Voyager 2 also headed outward, angled southward relative to the plane of the solar system, on a trajectory that would eventually carry it into interstellar space from a different direction than its twin. By the late 1980s, both spacecraft had entered what NASA designated the Voyager Interstellar Mission. The new objective was to fly outward until they crossed the edge of the Sun's protective influence and to measure whatever they found on the other side. The distances involved resist intuitive understanding. 1 astronomical unit is the distance from Earth to the Sun, approximately 93 million miles. Voyager 1 currently sits at roughly 163 astronomical units from the Sun. Multiply 93 million by 163, and the result exceeds 15 billion miles. Voyager 2 trails behind at approximately 137 astronomical units, or roughly 12 billion miles out. Both spacecraft continue moving outward at speeds that would carry them across the entire continental United States in approximately 5 minutes. At interstellar distances, this is still glacially slow. When news headlines declared that Voyager 1 had left the solar system, they were using a phrase that requires careful qualification. The solar system, defined by the Sun's gravitational dominance, extends enormously farther than Voyager has travelled. The Oort cloud, a vast theoretical shell of icy bodies loosely bound to the Sun by gravity, is believed to begin at roughly 2,000 astronomical units from the Sun and extend outward to perhaps 100,000 astronomical units. Voyager 1 has not reached the inner edge of this structure. At its current speed, it would take approximately 500 years to reach the Oort cloud's inner boundary, and roughly 30,000 years to pass through the cloud entirely. By the definition of gravitational dominance, Voyager remains inside the solar system and will be for tens of thousands of years. What Voyager actually crossed was something different and in many ways more significant than the gravitational boundary. It crossed the heliosphere. The heliosphere is the region of space controlled by the solar wind. Every second, without pause, the Sun exhales roughly 1.5 million tons of charged particles into space. Protons, electrons, and heavier ions torn from the solar corona by temperatures exceeding 1 million degrees Celsius stream outward in every direction at speeds ranging from 300 to 800 kilometers per second. This continuous flow is called the solar wind, and it carries with it the Sun's own magnetic field, stretched and twisted by solar rotation into a vast spiraling structure called the Parker spiral. After the physicist Eugene Parker, who predicted its existence in 1958, the solar wind inflates an enormous bubble around the Sun, pushing against the pressure of the interstellar medium, the thin gas, dust, and magnetic fields that fill the space between stars. Where the outward pressure of the solar wind balances the inward pressure of the interstellar medium, a boundary forms. That outermost boundary is called the heliopause. Inside the heliopause, the magnetic field is solar in origin. The dominant charged particles are solar wind ions. The radiation environment is modulated by our star's activity and its 11-year cycle. Outside the heliopause, the Sun's control ends. The crossing from solar territory to interstellar space does not happen all at once. It occurs in stages that Voyager documented methodically over decades. The first stage is called the termination shock. As the solar wind flows outward, it gradually thins. The density drops with the square of the distance from the Sun. At Earth's orbit, the wind density is roughly 5 to 10 particles per cubic centimetre. At Neptune's distance of 30 astronomical units, it has dropped to roughly 1/10 of a particle per cubic centimetre. But the wind remains supersonic until it hits the termination shock, the point where the interstellar medium's pressure becomes significant enough to force the solar wind to decelerate abruptly from supersonic to subsonic speed. Voyager 1 crossed the termination shock in December of 2004 at a distance of approximately 94 astronomical units from the Sun. The shock was not a smooth, symmetric shell. It was an uneven, fluctuating surface that Voyager passed through multiple times as the boundary rippled back and forth across the spacecraft's position. The temperature of the post-shock material exceeded 100,000 Kelvin as kinetic energy converted into thermal energy. Voyager 2 crossed the termination shock in August of 2007 at approximately 84 astronomical units, 10 astronomical units closer to the Sun than its twins crossing. This asymmetry confirmed that the heliosphere is not a perfect sphere. The solar system moves through the galaxy at roughly 230 kilometers per second, and the interstellar medium pushes harder against the leading side of the heliosphere than the trailing side. Beyond the termination shock, both spacecraft entered the heliosheath, a thick, turbulent buffer zone where the slowed solar wind piles up, heats, and churns before reaching the heliopause. The heliosheath proved far stranger than anticipated. Magnetic field lines folded back on themselves and formed large-scale magnetic bubbles that trapped and released energetic particles unpredictably. Temperatures rose dramatically. The heliosheath was neither fully solar nor fully interstellar, a transition zone where two vast physical systems pressed against each other across tens of billions of miles. Then, in the summer of 2012, Voyager 1's instruments began registering the final transition. The low-energy charged particle instrument and the cosmic ray subsystem, two detectors that had been faithfully counting particles for 35 years, showed a dramatic shift. The flux of anomalous cosmic rays, particles accelerated at the termination shock within the heliosphere, dropped precipitously over just a few days. Simultaneously, the count of galactic cosmic rays, high-energy particles, originating from sources scattered throughout the Milky Way, surged upward. The solar particle population vanished. The galactic population arrived. The transition was stark, but the magnetic field data complicated the picture. Scientists had expected a sharp rotation in the magnetic field direction at the heliopause, a clean switch from the solar field orientation to the interstellar field orientation. Instead, the field direction changed gradually over a period of days to weeks. The debate about whether Voyager had truly crossed the heliopause played out in journals and at conferences throughout 2012 and into 2013. The resolution came from an unexpected source. In early 2012, a powerful coronal mass ejection erupted from the Sun. This massive burst of solar plasma and magnetic field raced outward through the heliosphere at speeds exceeding 1,000 kilometers per second. Months later, the shockwave from this eruption reached Voyager 1's location, more than 120 astronomical units from the Sun. When the shockwave arrived, it caused the plasma surrounding the spacecraft to vibrate at specific frequencies. Voyager 1's plasma wave science instrument, one of the few still receiving enough power to operate, detected these oscillations clearly. The frequency of plasma oscillations depends directly on the density of the surrounding material. Higher density produces higher frequency. When scientists analyzed the data, they calculated a plasma density of approximately 0.08 electrons per cubic centimeter. This was roughly 40 times denser than the plasma in the outer heliosheath. The measurement was decisive. Voyager 1 was surrounded by material far too dense to be solar wind plasma. It was immersed in the interstellar medium. Working backward through the particle data, the magnetic field records, and the plasma wave measurements, scientists pinpointed the crossing. Voyager 1 had passed through the heliopause around August 25, 2012, at a distance of approximately 121.7 astronomical units from the Sun. The announcement came in September of 2013, more than a year after the actual event. For those 13 months, Voyager 1 had been in interstellar space without anyone on Earth being certain. Voyager 2 confirmed and expanded the discovery 6 years later. On November 5, 2018, at a distance of approximately 119 astronomical units, Voyager 2 crossed the heliopause. Its crossing was in some ways even more scientifically valuable than its twins, because Voyager 2 still carried a functioning plasma science instrument that could directly measure the properties of charged particles in the surrounding medium. Voyager 1's equivalent instrument had failed in 1980, nearly 4 decades before its heliopause crossing. Everything Voyager 1 knew about the plasma around it had to be inferred indirectly from plasma wave oscillations. Voyager 2 could measure the plasma directly, providing density, temperature, speed, and composition data that its twin simply could not. The plasma science instrument confirmed what the plasma wave data had suggested. At the heliopause, the solar wind plasma disappeared abruptly. One moment, Voyager 2 was immersed in outward-flowing solar material. The next, that flow had ceased entirely, and the spacecraft was surrounded by a denser, hotter, and essentially stationary plasma of interstellar origin. The transition was sharp. The contrast between the two environments was unambiguous. 2 spacecraft, 2 independent crossings from different directions. 2 complete sets of instruments recording the same fundamental transition at different times. The scientific case was airtight. The heliosphere has a definable outer boundary. That boundary can be crossed, and beyond it lies a physical environment that is measurably, fundamentally different from everything within the Sun's domain. The instruments aboard those 2 aging spacecraft produced the first direct measurements of the local interstellar medium. Every number in the dataset carries implications. Start with the most basic finding: what the particle environment actually looks like once the sun's protection ends. Voyager 1 carries two instruments capable of detecting energetic charged particles. The cosmic ray subsystem measures higher energy particles, those with energies above roughly 1 million electron volts. The low energy charged particle instrument covers a broader range, including lower energy ions and electrons. Together, they function as a particle census. Inside the heliosphere, both instruments had spent decades recording a population dominated by solar origin particles and by anomalous cosmic rays. Atoms from the interstellar medium that had drifted into the heliosphere become ionized by solar ultraviolet radiation and then been accelerated to high energies at the termination shock. When Voyager 1 crossed the heliopause, the anomalous cosmic ray population vanished, not gradually, not partially. It dropped to near zero within a matter of days. These particles exist only inside the heliosphere because they require the termination shock to reach their observed energies. Outside the heliopause, the acceleration mechanism is gone. Replacing the anomalous cosmic rays was the unmoderated population of galactic cosmic rays. These particles originate from sources scattered throughout the Milky Way, primarily from supernova remnants, but also from pulsars, binary star systems, and other energetic phenomena. They have been bouncing through the galaxy's tangled magnetic field for timescales that can reach millions of years. By the time they arrive at any given location in interstellar space, their directional information has been almost entirely scrambled. They come from every direction simultaneously, an isotropic rain of high-energy particles with no preferred source direction. Voyager 1's cosmic ray subsystem recorded the galactic cosmic ray intensity climbing to a level roughly 2 to 3 times higher than the maximum values ever observed inside the heliosphere during the deepest solar minimum. This is the baseline of interstellar space. This is what the galactic medium delivers continuously, regardless of solar activity, regardless of the 11-year cycle, regardless of anything the sun does. But the increase was not uniform across all energies. For cosmic rays in the lower energy range, below roughly 200 million electron volts per nucleon, the increase was far more dramatic. These are the particles most effectively blocked by the heliosphere's magnetic shielding. Inside the heliosphere, even during solar minimum, the flux of these lower energy galactic cosmic rays is suppressed by factors of 5 to 10 compared to interstellar values. Once Voyager crossed the heliopause, these particles appeared in abundance for the first time. The instrument registered flux levels it had never seen during the spacecraft's entire 35-year journey through the heliosphere. This low-energy cosmic ray population matters because it represents the component most efficiently absorbed by matter. When a lower-energy cosmic ray proton strikes a material surface, it deposits its energy over a shorter distance than a higher-energy particle. The ionization density along its track is higher. The damage per unit path length is greater. For biological tissue, lower-energy cosmic rays contribute disproportionately to radiation dose precisely because they are more readily absorbed. Understanding why the heliosphere suppresses this radiation so effectively requires understanding what cosmic rays are and where they come from. The galaxy is saturated with them. Galactic cosmic rays are not electromagnetic radiation like visible light or radio waves. They are physical particles, mostly protons but also helium nuclei, carbon, oxygen, silicon, iron, and other heavier atomic nuclei, traveling at velocities that approach the speed of light. The energy of individual galactic cosmic ray particles spans an extraordinary range. At the low end, they carry energies of a few million electron volts, comparable to particles produced in medical imaging equipment. At the high end, the most energetic cosmic rays ever detected carry energies exceeding 100 billion electron volts concentrated into a single subatomic particle. A proton at that energy carries the kinetic energy equivalent of a professionally thrown baseball compressed into a space smaller than an atomic nucleus. Most cosmic rays originate from supernova remnants. When a massive star exhausts its nuclear fuel and explodes, the resulting shockwave expands outward through the interstellar medium at thousands of kilometers per second. This shock persists for thousands of years, and particles trapped in the magnetic turbulence at the shock front get accelerated through a process called diffusive shock acceleration. Particles bounce back and forth across the shock boundary, gaining energy with each crossing, and over thousands of years, this mechanism produces the high-energy cosmic ray spectrum observed throughout the galaxy. Other sources contribute as well. Pulsars, the rapidly spinning neutron stars left behind after certain supernovae, generate intense rotating magnetic fields that accelerate particles to high energies in their magnetospheres. Binary star systems, where material transfers between companions, produce shocks and magnetic environments capable of particle acceleration. At the largest scales, the supermassive black holes at the centers of active galaxies generate jets of relativistic plasma that produce the highest energy cosmic rays observed. Particles so energetic they may originate from other galaxies entirely and travel across millions of light-years of intergalactic space before reaching the Milky Way. The heliosphere blocks the majority of these particles from reaching the inner solar system. The shielding mechanism is electromagnetic. Galactic cosmic rays are electrically charged. When a charged particle enters a magnetic field, it experiences a force perpendicular to both its velocity and the field direction. This force curves the particle's path. In the complex, turbulent, magnetic environment of the heliosphere, incoming cosmic rays encounter a constantly shifting maze of magnetic field lines carried outward by the solar wind. Lower energy cosmic rays, which have smaller momentum and are more easily deflected, get scattered repeatedly. Many are turned around entirely, reflected back into interstellar space before they penetrate to the inner solar system. Estimates, based on both modeling and direct measurement, indicate that the heliosphere reduces the galactic cosmic ray flux reaching the inner solar system by approximately 70 to 75% compared to the unshielded interstellar value. For lower energy cosmic rays, those below roughly 1 billion electron volts per nucleon, the suppression is even more dramatic, with the heliosphere excluding the vast majority and reducing their flux by factors of 10 or more. This is not a minor effect. It is the difference between a radiation environment that permits complex chemistry and one that systematically degrades it. Now turn to what Voyager measured once it was on the other side of this shield. The magnetic field did not disappear. This was itself a finding worth noting. Some early conceptions of the heliopause imagined a transition from a magnetized interior to a relatively unmagnetized exterior. The reality proved entirely different. The interstellar medium carries its own magnetic field, generated and sustained by currents flowing through the galactic plasma, compressed and shaped by shock waves from supernovae, sculpted by the motion of stars and gas clouds over millions of years. This galactic magnetic field has a typical strength in the solar neighborhood of roughly 0.3 to 0.5 nanotesla, actually somewhat stronger than the exhausted solar field in the outer heliosheath. Voyager 1 measured this transition directly. The field strength increased modestly across the heliopause boundary, from roughly 0.2 nanotesla inside to roughly 0.4 to 0.5 nanotesla outside. More importantly, the field direction changed. The interstellar magnetic field in our local galactic environment runs at an angle significantly different from the solar equatorial field that dominates inside the heliosphere. Voyager's magnetometer tracked this directional shift, recording a rotation in the field vector that confirmed the spacecraft had entered a magnetically distinct domain. However, the directional transition was not as clean as many models had predicted. Rather than a sharp pivot from solar to interstellar orientation, the data showed a more gradual rotation occurring over days to weeks. This indicated that the heliopause is not a mathematical surface of zero thickness, but a finite transition layer, where solar and interstellar magnetic fields intermingle. The two field systems coexist across this layer, which the spacecraft traversed over a physical distance of roughly a fraction of an astronomical unit. This finding suggested that the heliopause permits limited interchange of particles and field between the heliosphere and the interstellar medium, a partial permeability that had been suspected from theoretical models, but never confirmed by direct measurement until Voyager provided the evidence. After crossing the heliopause, Voyager 1 did not enter a perfectly static magnetic environment. The field showed fluctuations in both strength and direction on timescales of hours to days. These fluctuations reflect turbulence in the interstellar plasma, driven by processes operating on scales much larger than the spacecraft could directly sample. The interstellar medium is stirred by shock waves from distant supernovae, by the relative motion of interstellar clouds, and by magnetohydrodynamic instabilities inherent to any conducting fluid threaded by magnetic fields. Voyager 2's crossing in 2018 added a dimension that its twin could not provide. Where Voyager 1 had been forced to infer plasma properties indirectly through oscillation frequencies, Voyager 2 could sample the interstellar plasma with the precision of a direct measurement. At the heliopause crossing, Voyager 2's plasma science instrument detected an abrupt disappearance of the outward-flowing solar wind plasma. Inside the heliosheath, the instrument had been measuring a decelerated but still flowing solar wind with a speed of roughly 100 to 150 kilometers per second and a density of approximately 0.001 particles per cubic centimeter. At the boundary, this flow ceased. In its place, the instrument detected a plasma population that was denser, hotter in terms of particle kinetic energy, and essentially stationary relative to the spacecraft. The density measured by Voyager 2's plasma science instrument in the interstellar medium was approximately 0.05 to 0.06 electrons per cubic centimeter. This represented an increase of roughly 20 to 40 times over the solar wind density in the outer heliosheath. Context is essential here. By any terrestrial standard, this is still an extraordinarily thin medium. Earth's atmosphere at sea level contains approximately 25 quintillion particles per cubic centimeter. Even the best laboratory vacuum chambers contain trillions of particles per cubic centimeter. The interstellar medium at 0.05 particles per cubic centimeter is by human experience indistinguishable from perfect emptiness, but it is not emptiness. The difference between the heliosheath's thousandth of a particle per cubic centimeter and the interstellar medium's density is physically significant. Denser plasma transmits electromagnetic disturbances differently. It supports different wave modes. It interacts more strongly with magnetic fields. It exerts more pressure. The density jump at the boundary is the physical manifestation of the interstellar medium confining the heliosphere from the outside. The temperature measurement added another piece to the portrait. Voyager 2's plasma science instrument measured the interstellar plasma temperature at approximately 30,000 to 50,000 Kelvin. This requires careful interpretation. Temperature in plasma physics refers to the average kinetic energy of particles. A plasma at 50,000 Kelvin contains particles moving at speeds of roughly 20 to 30 kilometers per second. This is fast by everyday standards, but slow compared to the cosmic ray particles sharing the same space, which travel at significant fractions of the speed of light. The critical nuance is that despite the high temperature, the thermal energy density of the interstellar plasma is vanishingly small because so few particles are present. You could immerse your hand in plasma at 50,000 Kelvin in the interstellar medium and feel nothing because so few particles would actually strike your skin per second that the total energy transfer would be negligible. Temperature without density produces no perceptible heat, but the temperature is physically meaningful because it reflects the energy state of the medium. Plasma at 50,000 Kelvin has been heated by something. That something includes ancient shock waves from supernovae, turbulent dissipation of magnetic energy, and the general thermodynamic history of the local interstellar medium over millions of years. Beyond the direct particle and field measurements, Voyager 1's plasma wave science instrument provided a continuous record of the ambient plasma conditions through a different method. This instrument detects electromagnetic oscillations in the surrounding plasma, vibrations at frequencies determined by the local electron density. In the interstellar medium, the instrument recorded a persistent, low-frequency plasma oscillation at roughly 2 to 3 kHz. This faint signal represented the natural oscillation frequency of the interstellar plasma at its measured density, a kind of electromagnetic background tone produced by the medium itself. When NASA released an audio rendering of this signal in 2013, converting the plasma wave frequencies into the range of human hearing, the result was striking. A thin, steady tone rising and falling slightly as the plasma density fluctuated. The scientific community emphasized that the audio rendering was a translation, not a literal recording of sound waves. The interstellar medium is far too thin to support acoustic vibrations in the conventional sense. What Voyager detected were oscillations in the electric field of the plasma, electromagnetic phenomena rather than mechanical pressure waves. But the underlying physics was genuine. The interstellar medium vibrates at a characteristic frequency determined by its electron density, and Voyager's instrument detected that vibration directly. The hum proved scientifically valuable beyond its symbolic power. It provided continuous density tracking even during the long, quiet periods between solar-driven disturbances. Coronal mass ejections from the Sun occasionally send shock waves rippling outward through the heliosphere and into the near interstellar medium. When these shock waves reach Voyager's location, they cause the local plasma to oscillate more intensely, producing spikes in the plasma wave data that allow precise density calculations. Between these events, the quiet hum provides a baseline, a continuous background measurement that reveals the ambient state of the medium without requiring any external stimulus. The hum confirmed that the interstellar plasma density remains relatively stable over the timescales Voyager has been monitoring, hovering near 0.05 to 0.01 electrons per cubic centimeter. But within that stability, the data showed modest fluctuations, gentle rises and falls, that correspond to small-scale density structures in the local medium. These variations suggest that the interstellar medium in our neighborhood is not perfectly homogeneous. Density ripples exist on scales of astronomical units, driven by the same turbulent processes detected by the magnetometer. The medium breathes subtly and slowly in a rhythm set by forces that have nothing to do with our Sun. Taken as a whole, the measurements from both spacecraft produce a coherent, detailed, and unprecedented portrait of the local interstellar medium. The particle environment is dominated by galactic cosmic rays arriving from all directions with a flux 2 to 3 times the highest levels ever recorded inside the heliosphere. Lower energy cosmic rays, the component most effectively excluded by heliospheric shielding, are present in abundances 5 to 10 times greater than inside the bubble. The anomalous cosmic ray population, a product of the heliosphere's internal physics, is absent. The particle census has shifted entirely from solar to galactic. The magnetic field is galactic in origin, oriented differently from the solar field, slightly stronger than the exhausted field in the outer heliosheath, and permeated by turbulent fluctuations on multiple timescales. The boundary between solar and galactic magnetic domains is not a knife edge, but a finite transition layer where the two field systems blend. The plasma is denser than the material in the outer heliosphere by a factor of 20 to 40, warmer in terms of particle kinetic energy, and essentially stationary relative to the spacecraft. And it hums at a characteristic frequency that serves as a continuous monitor of ambient conditions. None of these conditions were fully anticipated before Voyager arrived to measure them. Models of the interstellar medium built from decades of remote astronomical observation had captured the broad strokes. Scientists knew the interstellar medium was thin, magnetized, and permeated by cosmic rays. But the specific values differed from many pre-crossing predictions in ways that mattered. The plasma density at the heliopause was slightly higher than several widely cited models had estimated. The magnetic field transition was more gradual than the clean directional flip that most simulations produced. The cosmic ray flux distribution in the lowest energy ranges showed a steeper increase than some models predicted. Each of these discrepancies was individually modest. None represented a dramatic failure of theory. But collectively, they demonstrated something that scientists already knew in principle, but could now confirm in practice. Remote observation can constrain the possibilities. Only direct sampling can select the truth. Models of the interstellar medium, however sophisticated, are built on assumptions about conditions at a location that had never been visited, Voyager visited. And the truth, as measured truth often does, proved more complicated and more interesting than the models had suggested. The truth is not the peaceful, inert, empty void that casual language suggests when people say the space between stars. The interstellar medium is an active environment. It is irradiated continuously by galactic cosmic rays carrying energies that range from millions to billions of electron volts per particle. It is threaded by a magnetic field shaped by galactic-scale processes operating over millions of years. It is mildly turbulent, with density and magnetic fluctuations that reflect the ongoing dynamical evolution of the gas and dust between stars. It is cold in the sense that any macroscopic object placed within it would radiate away its thermal energy and equilibrate at a temperature close to absolute zero, the ambient temperature of the cosmic microwave background at roughly 2.7 Kelvin. This last point deserves careful attention. The cosmic microwave background is the residual thermal radiation from the early universe, permeating all of space at essentially uniform intensity. Far from any star, an unheated object radiates its thermal energy into this background and equilibrates at approximately 2.7 Kelvin, roughly negative 270 degrees Celsius. At this temperature, most lubricants solidify, battery electrolytes freeze, structural metals become brittle, electronic components designed for the temperature ranges encountered inside the heliosphere cease functioning. Maintaining a habitable temperature inside a spacecraft requires continuous heating, which requires continuous power. This brings us to what the Voyager data means for the most ambitious question human civilization has ever seriously considered: whether it is physically possible to send a spacecraft, or ultimately a crewed vehicle, between the stars. These measurements are not merely academic. Every particle count and field strength and density estimate carries implications for interstellar travel. The answer to that question depends not only on how far the stars are, but on what lies between them. Voyager has now told us in hard data what that something is. Every vehicle humanity has ever launched, every astronaut who has ever flown, every satellite that has ever orbited any planet has operated within the heliosphere. We have never maintained a functioning presence outside this bubble, except through the 2 Voyager spacecraft. And those 2 spacecraft are the only instruments we have ever placed in that environment. When their power runs out, as it will within the next several years, we will have no presence in interstellar space at all. Consider what the interstellar environment means for spacecraft engineering. Every vehicle humanity has ever sent into space carries assumptions baked into every specification. The radiation models presuppose the heliosphere's shielding. The thermal budgets assume proximity to a star. The power systems rely on solar energy or radioactive fuel that will be exhausted long before any interstellar crossing could be completed. Remove all of these assumptions simultaneously, and you are left with a design problem that no existing spacecraft architecture can solve. Radiation shielding is the most immediate challenge. Galactic cosmic rays arrive from every direction with energies spanning from millions to billions of electron volts per nucleon. The most common cosmic ray particles are protons, but the flux includes helium nuclei, carbon, oxygen, silicon, iron, and other heavy ions, all traveling at substantial fractions of the speed of light. When these particles strike a spacecraft hull, they do not simply bounce off or get absorbed cleanly. They interact with the nuclei of the shielding material, producing cascades of secondary particles, neutrons, protons, pions, muons, and gamma rays that spray inward from the impact site, sometimes depositing more total energy inside the spacecraft than the original cosmic ray would have delivered on its own. This secondary particle production is one of the most stubborn facts of radiation physics. For galactic cosmic rays above certain energies, adding more aluminum shielding actually increases the dose to anything inside rather than decreasing it. The shield becomes a particle multiplier. Researchers at NASA and other agencies have studied alternative shielding materials for decades. Hydrogen-rich compounds perform better than metals because hydrogen nuclei are close in mass to incoming protons, allowing more efficient energy transfer that degrades the cosmic ray's energy without producing heavy secondary fragments. Polyethylene, water, and even liquid hydrogen have been proposed as shielding materials. The best estimates suggest that optimized hydrogen-rich shielding can reduce the galactic cosmic ray dose by roughly 30 to 50%. This is meaningful but insufficient for a journey lasting decades. A crew exposed to even half the unshielded interstellar cosmic ray intensity for 20 or 30 years would accumulate radiation doses far exceeding the career limits established by every major space agency. The cancer risk alone would be substantial. The potential for central nervous system degradation, cardiovascular damage, and cataract formation adds further layers of concern. Active shielding concepts using powerful superconducting magnets to generate an artificial magnetosphere around a spacecraft have been proposed as alternatives. The idea mimics what the heliosphere does naturally, using magnetic fields to deflect incoming charged particles before they reach the hull. The physics is sound, the engineering is formidable. Generating a magnetic field strong enough to deflect galactic cosmic rays with energies of billions of electron volts would require superconducting coils of enormous size, carrying currents that would produce intense magnetic fields. Throughout the spacecraft's interior, the mass and power requirements of such a system, using any technology that currently exists or is plausibly foreseeable, would dominate the spacecraft's total mass budget. And the field would need to be sustained continuously for the entire journey, without interruption, without failure, without degradation, for decades. Energy is the next fundamental problem. Inside the heliosphere, spacecraft can use solar panels out to roughly 5 astronomical units, beyond which the solar flux becomes too weak for practical power generation. Radioisotope thermoelectric generators extend the range much farther, as the Voyagers have demonstrated, but their power output decays steadily as the radioactive fuel decays. Plutonium-238, the isotope used in Voyager's generators, has a half-life of approximately 87.7 years. After one half-life, the power output drops by half. A journey to the nearest star at Voyager, one's current velocity of roughly 17 kilometers per second, would require more than 73,000 years. That corresponds to roughly 800 half-lives of plutonium-238. The fuel would be completely exhausted within a few centuries, leaving the spacecraft without power for the overwhelming majority of the transit. Nuclear fission reactors offer higher power output and could potentially last for decades, but even fission fuel is finite. Uranium or thorium reactors would need to be designed for operational lifetimes, far exceeding anything ever built on Earth, where the longest operating reactors have functioned for roughly 60 years with extensive maintenance and human intervention. A reactor on an interstellar spacecraft would need to operate autonomously, without maintenance, without refueling, and without spare parts, for a duration that would strain any engineering margin. The interstellar medium itself offers no alternative energy source. There is no sunlight to collect. The particle density is far too low to fuel any conceivable ram scoop at the speeds a spacecraft would need to travel. The magnetic field energy density is negligible. The thermal energy of the plasma, spread across such extraordinary volumes at such low density, is thermodynamically inaccessible. An interstellar spacecraft would carry every joule of energy it will ever use from departure to arrival with no possibility of resupply. Set aside the propulsion problem entirely. Assume that some future civilization solves it. Assume they can accelerate a spacecraft to 10% of the speed of light and sustain that velocity for decades. At that speed, reaching Alpha Centauri, the nearest star system at approximately 4.3 light-years, would require approximately 43 years. During every one of those years, the vehicle would be immersed in the environment Voyager measured. Full cosmic ray flux, no solar power, temperatures near absolute zero unless continuously heated, no shelter, no harbour, no possibility of rescue or resupply. 10% of the speed of light corresponds to roughly 30,000 kilometers per second, nearly 2,000 times faster than Voyager 1. Achieving this speed with a spacecraft massive enough to carry meaningful payload, let alone a human crew, would require energy inputs that dwarf any propulsion system ever built. Chemical rockets are entirely inadequate. Ion drives, solar sails, and nuclear thermal propulsion all fall short by orders of magnitude. Only concepts like nuclear pulse propulsion, antimatter engines, or laser-driven light sails even approach the theoretical capability. None of these have progressed beyond preliminary design studies, and the engineering challenges of building, testing, and operating any of these systems reliably enough for a decades-long interstellar journey remain immense. The distance is not the only barrier, the medium is. This realization extends far beyond human engineering. It applies to every star system in the galaxy. The Milky Way contains somewhere between 200 billion and 400 billion stars. Each star that produces a stellar wind, which includes most stars on the main sequence, inflates its own protective bubble analogous to our heliosphere. These astrospheres vary enormously in size and effectiveness. Massive hot stars with powerful winds create large astrospheres that may extend hundreds of astronomical units. Small red dwarfs with feeble winds produce astrospheres that may barely encompass their habitable zones. But regardless of the size of any individual astrosphere, the space between those bubbles is filled with the interstellar medium. Every star system in the galaxy is an island surrounded by this ocean. The astrospheres are harbours. The interstellar medium is the open water, and the open water is hostile. The volume of the galaxy occupied by astrospheres is vanishingly small compared to the total volume. If you could somehow inventory the entire Milky Way, adding up every stellar wind bubble around every star, the combined volume of all those protected regions would represent a tiny fraction of the galaxy's total volume. The overwhelming majority of the Milky Way, measured by volume, consists of the interstellar medium, the thin gas, the magnetic fields, the cosmic rays, the cold, the emptiness. That is what the galaxy is made of. Stars and their protective bubbles are rare exceptions, oases scattered across a desert that stretches 100,000 light-years from edge to edge. This perspective inverts the common image of our galaxy. When people picture the Milky Way, they imagine a luminous spiral of stars, dense and glittering, a cosmic city full of potential destinations. The reality is closer to a vast, dark, irradiated wilderness with tiny campfires scattered impossibly far apart. The campfires are real, the stars are there, but the wilderness between them is the dominant feature, and Voyager has measured its hostility firsthand. Every civilization that might exist in the galaxy, if any others do exist, faces the same barrier. They sit inside their own stellar bubble, shielded from the galactic environment by their own star's wind. If they look outward and dream of reaching the next star, they confront the same interstellar medium that Voyager measured, the same cosmic ray flux, the same absence of energy sources, the same thermal hostility, the same radiation-saturated void stretching light years in every direction. The physics does not change depending on who you are or what star you orbit. The interstellar medium is the same ocean for every island. This has implications for one of the most famous questions in science. If the galaxy contains billions of potentially habitable planets, and if even a small fraction of those develop technological civilizations, where is everyone? The Fermi paradox, the tension between the apparent probability of extraterrestrial intelligence and the absence of any confirmed evidence for it, has generated dozens of proposed solutions over the decades. Some invoke the rarity of intelligence itself. Some propose self-destruction as a universal fate for technological species. Some suggest that civilizations exist but choose not to communicate. Voyager's data offers a different, more physically grounded contribution to this conversation. The interstellar medium is not a highway connecting civilizations. It is a barrier separating them. Every star system is enclosed within its protective bubble, surrounded by a medium that punishes anything that ventures into it. Crossing that medium is not merely a matter of sufficient speed or fuel. It is a matter of surviving an environment that continuously degrades, irradiates, and drains any object that enters it. The silence of the galaxy may not reflect the absence of other civilizations. It may reflect the reality that the space between civilizations is a far more formidable obstacle than distance alone suggests. Light and radio waves cross the interstellar medium with relative ease. Electromagnetic signals propagate freely through the thin plasma, attenuated by distance and slightly dispersed by free electrons, but fundamentally capable of bridging the gaps between stars. The round-trip signal delay to the nearest star exceeds 8 years, but communication across interstellar distances is physically possible. Sending a physical object, a probe or a ship, requires surviving the medium rather than merely passing a signal through it. That is a categorically different challenge. The distinction between sending a signal and sending an object illuminates something important about our galaxy. The Milky Way may be a place where information can travel between star systems, but where matter effectively cannot, at least with any technology operating within the limits we currently understand. Civilizations might detect each other's signals across hundreds or thousands of light years, while remaining permanently unable to visit each other in person. The galaxy could be full of voices and empty of visitors, full of knowledge and devoid of contact. Every civilization, an island, able to see the distant campfires of others, but unable to reach them through the hostile ocean that separates every star from its neighbors. There is another dimension to the heliosphere's protection that Voyager's crossing makes vivid. The heliosphere is not static, and it has not always been the size it is today. Right now, the Sun and its planets are passing through a region of the interstellar medium called the local interstellar cloud, a relatively warm, moderately dense patch of partially ionized gas, roughly 30 light-years across. The properties of this cloud determine the external pressure pushing against the heliosphere. The density of the local interstellar cloud is approximately 0.1 to 0.3 particles per cubic centimeter, and its temperature is roughly 6,000 to 8,000 Kelvin. These are the conditions Voyager measured just outside the heliopause. They are the conditions that currently define how far the heliosphere extends. But the local interstellar cloud is not the only structure in our galactic neighborhood. The solar system is located near the edge of this cloud, and within the next few thousand to tens of thousands of years, it will likely exit into a different region. Some models suggest the Sun may enter an area of lower density material, which would allow the heliosphere to expand. Other models suggest the Sun could encounter a denser cloud, which would compress the heliosphere inward. Scientists have found evidence that this has happened before with measurable consequences. Studies of deep-sea sediments and Antarctic ice cores have detected elevated concentrations of the isotope iron-60, a radioactive atom produced in supernova explosions and delivered to Earth by interstellar dust. These deposits suggest that the solar system passed through regions of enhanced interstellar material roughly 2 to 3 million years ago, and again around 7 to 8 million years ago, potentially debris from relatively nearby supernovae that temporarily increased the density of the local interstellar medium. A denser interstellar medium compresses the heliosphere. If the external pressure increased sufficiently, the heliopause could be pushed inward from its current distance of roughly 120 astronomical units to perhaps 60 or 70 astronomical units, or even closer. At those distances, the outer planets would remain inside the heliosphere, but the shielding for the entire solar system would be reduced. More galactic cosmic rays would penetrate to the inner solar system, increasing the radiation dose on every planetary surface and in every planetary atmosphere. A study published in the journal Nature Astronomy in 2024 explored a more extreme scenario. Researchers modeled what would happen if the solar system encountered a particularly dense cold cloud, one with a density of roughly 1,000 to 3,000 particles per cubic centimeter, far denser than the material currently surrounding our heliosphere. Under those conditions, the heliosphere could be compressed so dramatically that it would shrink inside Earth's orbit. Our planet would be directly exposed to the interstellar medium. The galactic cosmic ray flux at Earth's surface would increase by roughly an order of magnitude. The researchers suggested this may have actually occurred roughly 2 million years ago, correlating with geological evidence from the same period. Ice core data shows a notable increase in cosmic ray indicators during that epoch. The timing overlaps with the beginning of a series of glaciation events in Earth's recent geological history. Whether the heliospheric compression directly contributed to climate change remains debated and unconfirmed, but the physical mechanism is sound. More cosmic rays reaching the atmosphere can increase cloud nucleation, affecting cloud cover and planetary reflectivity. Changes in atmospheric chemistry from incoming interstellar gas could modify the greenhouse effect. The connection between heliospheric size and planetary conditions is not speculative. It is a matter of magnitudes and timescales. This variability transforms the heliosphere from a permanent feature of our solar system into a conditional one. It exists because the sun produces a wind, but its size and effectiveness depend on what that wind pushes against. Change the external conditions, and the shield changes with them. The protection we enjoy today is the product of a specific temporary equilibrium between a specific stellar wind and a specific interstellar environment. The solar system has orbited the galactic center roughly 20 times since the sun formed. Each orbit takes approximately 230 million years and carries us through different regions of the galactic disk. Some orbits pass through spiral arms where supernova rates are higher and the interstellar medium is denser and more turbulent. Other segments carry us through quieter interarm regions. The heliosphere breathes in response, expanding during quiet passages and contracting during turbulent ones. The heliosphere is not a fortress. It is a tent erected by the solar wind, held up by the continuous outpouring of charged particles from the corona, and pressed upon from all sides by an interstellar medium whose properties we do not control and cannot predict with certainty. The tent holds today. It has held for billions of years, with variations, but it is shaped by its environment, and that environment is not static. None of this will result in the heliosphere vanishing during the Sun's remaining main sequence lifetime. The Sun has roughly 5 billion years of hydrogen fuel remaining. As long as it burns, the solar wind will blow and the heliosphere will exist in some form. But when the Sun eventually exhausts its hydrogen and evolves into a red giant, its outer layers will expand enormously and the nature of its wind will change. When it finally sheds those layers and collapses into a white dwarf, the wind will cease. The heliosphere will dissipate. Whatever remains of the solar system will be exposed to the full interstellar medium for the first time since the Sun ignited 4.5 billion years ago. Red dwarfs, which constitute roughly 70% of all stars in the Milky Way, are small, cool, and produce relatively weak stellar winds. Their astrospheres may be significantly smaller than the Sun's heliosphere. Habitable zone planets orbiting red dwarfs sit so close to their host star that they remain within the astrosphere, but the margin is thin. A particularly active phase of the interstellar medium, perhaps a passing shock from a nearby supernova, could temporarily compress the astrosphere and expose those planets to enhanced cosmic ray fluxes. Heliospheric protection is not a universal feature of planetary systems. It depends on the host star's mass, age, and activity level, and on the properties of the local interstellar medium. Some planetary systems in the galaxy may exist with astrospheres that are barely effective, with habitable zone planets experiencing cosmic ray fluxes several times higher than Earth's. The heliosphere is not a luxury, it is infrastructure. It is the invisible architecture that makes the interior of our solar system a fundamentally different environment from the galaxy at large. These machines are old. The power sources aboard each Voyager spacecraft are decaying at a rate dictated by the 87.7-year half-life of plutonium-238. Each spacecraft's 3 radioisotope thermoelectric generators produced about 470 watts of electrical power at launch. Today they produce roughly 220 watts, and that number drops by approximately 4 watts every year. NASA has been systematically shutting down instruments and heaters to conserve what little power remains. The cameras were turned off in 1990. Science instruments have been deactivated one by one as the available power contracted around a smaller and smaller set of functioning sensors. The radio signals reaching Earth from Voyager 1 carry a transmitted power of roughly 23 watts at the source, transmitted through a 12-foot dish antenna aimed at a planet more than 15 billion miles away. By the time those signals reach the 70-meter dishes of NASA's Deep Space Network, the received power has fallen to roughly 110 billionths of a trillionth of a watt. Engineers can extract meaningful scientific data from a signal this feeble is a testament to decades of refinement in deep space communication techniques. The round-trip communication time now exceeds 45 hours. A command sent from Earth takes nearly 23 hours to arrive. The spacecraft's response takes another 23 hours to return. A single exchange requires nearly 2 full days of waiting. Within the next several years, sometime in the late 2020s or early 2030s, the power will no longer sustain any science instrument. The last heater will shut down. The last data stream will go silent. Voyager 1 and Voyager 2 will become inert objects, still racing outward at their current speeds, still carrying their instruments and their golden records, but no longer capable of sensing or reporting their environment. Voyager 1 will approach within about 1.6 light-years of the star Gliese 445 in the constellation Camelopardalis in approximately 40,000 years. It will not slow down. It cannot slow down. It will pass through that star's neighborhood and continue onward, a silent artifact from a civilization that once lived on a small rocky world, 26,000 light-years from the galactic center. Each Voyager carries a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, greetings in 55 languages, music spanning from Bach to Chuck Berry, the sound of wind and rain, and a human heartbeat, diagrams showing Earth's position relative to 14 pulsars, a cosmic address designed to remain valid for hundreds of millions of years. The record is mounted on the spacecraft's exterior, exposed to the full interstellar cosmic ray flux. Over tens of thousands of years, that radiation will gradually degrade the record's surface. The grooves that encode the audio will be slowly eroded by particle impacts. The images will blur. The gold plating will endure longer than most materials, but even gold is not immune to the steady rain of high-energy particles that Voyager's own instruments measured and reported. The message encoded with such care in 1977 will eventually become unreadable. The interstellar medium, indifferent and continuous, will erase it. Before that erasure, the data reached us, and the data describes something that changes how a person should understand their place in the cosmos. The heliosphere has been protecting this solar system for roughly 4.5 billion years. Every evolutionary step that led to complex life on Earth occurred within its shelter. Every species that has ever existed every ecosystem that has ever functioned, every molecule of DNA that has ever replicated on this planet, did so under the reduced cosmic ray flux that the heliosphere provides. We evolved inside the bubble. Until Voyager, we had no direct evidence of what conditions are like outside it. Now we do. The Voyagers did not discover aliens. They did not find wormholes or shortcuts. They did not encounter anything supernatural or inexplicable. What they found was something that no fiction had prepared us for. They found reality. The real, measured, physically confirmed conditions that prevail in the space beyond the sun's protection. Cold, irradiated, magnetically turbulent, empty of resources, devoid of shelter, stretching for light years in every direction before the faintest warmth of another star's influence could be detected. The space beyond the heliosphere is not the passive emptiness of popular imagination. It is not a benign void waiting to be traversed. It is a medium that degrades what enters it, not through drama or spectacle, but through the relentless accumulation of particle impacts, thermal drain, and the complete absence of any resource that a complex system requires to sustain itself. And it fills the overwhelming majority of the galaxy. We live inside a bubble. That bubble is inflated by an average star, maintained by a continuous outpouring of charged particles, and sustained by a nuclear fusion process that has been running for 4.5 billion years and will continue for roughly 5 billion more. Inside this bubble, the radiation is manageable. The temperatures, while extreme by human standards, are moderated by solar heating. The magnetic environment is organized by the sun's field. The conditions permit the existence of complex chemistry, liquid water, atmospheric retention, and biological evolution. Outside this bubble, none of those conditions hold. The radiation is galactic in origin and unshielded. The temperature for any passive surface approaches absolute zero. The magnetic field is alien in structure and turbulent in character. The medium offers no energy, no resources, and no shelter. Everything that makes the interior of our solar system hospitable traces back to the heliosphere's ability to hold the galaxy at bay. Voyager 1 and Voyager 2 will go silent within the next several years. The last data will arrive at the Deep Space Network, be decoded, archived, and studied, and then silence. The spacecraft will continue outward, cooling to the ambient temperature of the cosmic microwave background, drifting through the galaxy as inert artifacts. The data has been delivered. It describes something that should change how every person on Earth understands their place in the cosmos. We are not residents of a galaxy brimming with accessible destinations. We are inhabitants of a single protected enclave within a galaxy that is overwhelmingly composed of the hostile medium between stars. The stars themselves are distant beyond meaningful human experience. The medium between them is harsh beyond casual intuition. And the bubble that protects us is finite, maintained by a star that will not burn forever, wrapped around a solar system that occupies an infinitesimally small fraction of the Milky Way's total volume. There is something in the human spirit that looks at the night sky and sees possibility, destinations, worlds to explore, neighbors to find. This impulse is beautiful, and it is the same impulse that built the Voyager spacecraft, launched them on their decades-long journey, and kept scientists listening to their fading signals for nearly half a century. That impulse deserves respect. It may even deserve pursuit, but it must be pursued with honesty about what lies between here and there. The galaxy is not a map with roads connecting the dots. It is an archipelago of isolated islands in an ocean of radiation and emptiness. And the ocean is wider, colder, and more punishing than most people have ever been told. Voyager went into that ocean. It measured the currents, sampled the plasma, counted the particles, recorded the magnetic fields, and sent back the truth at a rate of 160 bits per second across 15 billion miles of space. The truth is that what lies beyond our solar system is not merely far, it is fundamentally hostile. The heliosphere is not just a boundary, it is a refuge. The sun is not just a star, it is a shield. And the most significant thing about what Voyager found is not that it traveled farther than any human object has ever gone. It is that everything it measured on the other side confirms what the numbers always suggested, but no instrument had ever verified. The galaxy, for all its grandeur and all its billions of stars, is made mostly of the space between those stars. And that space is no place for anything that depends on warmth, shelter, or the protection of a star to survive. The question of what comes next belongs to the species that built those two small machines. A species that lives on one world, orbiting one star, inside one bubble, in a galaxy that stretches 100,000 light years in every direction and is filled almost entirely with the very thing those machines were the first to touch, the first to measure, and the first to report back to the only home they ever knew. The sun will keep blowing its wind, the heliosphere will hold. Beyond it, the interstellar medium will continue as it has for billions of years, shaped by the slow violence of supernovae and the quiet drift of interstellar clouds, carrying the faint electromagnetic hum of its own physical identity across light years of cold space. Whether humanity ever finds a way to cross it is a question that remains open. What no longer remains open is the question of what it would require to try. To fully appreciate what Voyager measured, it is worth examining the heliosphere's protective function in more detail, particularly how the sun's continuous exhalation of charged particles actively reshapes the local galactic environment in ways that benefit every object inside the bubble. The solar corona presents one of the most persistent puzzles in solar physics. The surface of the sun, the photosphere, has a temperature of roughly 5,800 Kelvin. The corona, which lies above the surface, somehow reaches temperatures exceeding 1 million Kelvin. This is counterintuitive in the extreme. Moving away from a heat source, you expect temperatures to fall, not to rise by a factor of nearly 200. Scientists have proposed numerous mechanisms to explain this, including magnetic reconnection events, called nanoflares, in which small-scale magnetic field lines rapidly reconfigure and release energy, and the dissipation of magnetohydrodynamic waves propagating upward from the solar interior. The precise balance of processes that heat the corona remains an active area of research. But the consequence is settled physics. The corona is so ferociously hot that the sun's gravity cannot contain it. At 1 million degrees Celsius and above, the thermal energy of coronal particles exceeds the gravitational binding energy at the sun's surface. The result is a continuous, supersonic outflow that never stops as long as the sun burns. That outflow is the solar wind, and without it there would be no heliosphere, no protective bubble, and no moderation of the galactic cosmic ray environment inside our solar system. The solar wind is not a uniform flow. It emerges faster from coronal holes, regions where the sun's magnetic field lines open directly into space rather than looping back down to the solar surface. The fast wind from these regions can exceed 700 kilometers per second. The slow wind, which originates from regions where closed magnetic loops temporarily trap material before releasing it, averages around 300 to 400 kilometers per second. As the sun rotates approximately once every 27 days at its equator, the embedded magnetic field lines get wound into the Parker spiral structure that gives the heliosphere its internal magnetic architecture. The Parker spiral creates a three-dimensional magnetic web that extends outward through the entire solar system. Every planet, every asteroid, every comet, every grain of interplanetary dust sits within this spiraling structure. It is the skeleton of the heliosphere. The 11-year solar cycle modulates the strength and extent of this structure, with solar maximum producing a stronger, more turbulent wind that inflates the heliosphere slightly and increases the scattering of incoming cosmic rays, and solar minimum producing a weaker, more ordered wind that allows more galactic cosmic rays to penetrate inward. This cycle has been tracked continuously by ground-based neutron monitors for over 70 years and represents one of the most reliably measured phenomena in space physics. The heliosphere also protects against something less familiar than cosmic rays, but equally important over geological timescales: the erosion of planetary atmospheres by energetic particles. Without the heliosphere to deflect most of the solar wind and cosmic rays, the upper atmospheres of planets would be exposed to far higher particle fluxes. Energetic particles can ionize atmospheric molecules, stripping electrons and creating ions that can be swept away by the solar wind or accelerated out of the atmosphere by electric fields. This process, called atmospheric sputtering, operates even with heliospheric protection, but would be more severe without it. Mars, which lost much of its early atmosphere over billions of years partly through this mechanism, provides a cautionary example of what happens to a world with diminished magnetic and atmospheric protection. The heliosphere's influence on atmospheric chemistry extends to Earth as well. Galactic cosmic rays that penetrate the heliosphere and Earth's magnetosphere ionize molecules in the lower atmosphere, producing ions that can serve as condensation nuclei for cloud droplets. The relationship between cosmic ray flux, ionization rates, and cloud formation has been studied extensively, though the magnitude of the effect on Earth's climate remains debated. What is clear is that the heliosphere modulates the cosmic ray flux reaching Earth's atmosphere, and changes in heliospheric extent would change the ionization environment and potentially influence cloud formation rates. The broader picture painted by Voyager's measurements connects individual particle counts and field strengths to the question of what the galaxy looks like as an environment for complex life. Consider the timescales involved. Life on Earth has existed for roughly 3.5 billion years. Complex multicellular life emerged approximately 550 million years ago. The heliosphere has been present throughout all of this, reducing the cosmic ray flux at Earth's surface, maintaining a relatively stable radiation environment despite the solar system's continuous journey through different regions of the galactic disk. The heliosphere has breathed in and out in response to changing interstellar conditions, but it has never vanished. It has always been there, providing the shielding that permitted the slow, painstaking process of biological evolution to proceed without being derailed by catastrophic radiation events. This continuity of protection is not something that can be taken for granted across the galaxy. A star in a denser region of the galactic disk, where supernovae occur more frequently and the interstellar medium is more turbulent, would have its astrosphere compressed more aggressively and more often. Habitable zone planets around such stars would experience more frequent episodes of elevated cosmic ray exposure. The stability of Earth's biosphere over hundreds of millions of years owes something, possibly a great deal, to the relative quietude of our current galactic neighborhood and the consistency of the heliospheric protection it allows. Voyager's measurements of the local interstellar medium have also fed directly into models of cosmic ray propagation throughout the galaxy. Understanding how cosmic rays travel through the interstellar medium requires knowing the properties of the medium itself, particularly the turbulent spectrum of its magnetic fields. Cosmic rays scatter off magnetic irregularities as they travel, and the efficiency of that scattering depends on how the magnetic turbulence is distributed across different spatial scales. Voyager provided the first direct constraints on this turbulent spectrum in the very local interstellar medium, data that now feeds into models of how cosmic rays spread through the Milky Way as a whole. This matters because cosmic rays are not merely a radiation hazard, they are also a significant energy input into the interstellar medium. They heat the gas between stars. They ionize neutral atoms and molecules, enabling chemical reactions that would not otherwise occur in cold molecular clouds. They contribute to the pressure balance that determines how interstellar gas collapses to form new stars. The physics of cosmic rays is woven through the physics of star formation, which is woven through the physics of galaxy evolution. Voyager's measurements, however local, connect to processes operating at the largest scales. There is also the practical matter of designing future interstellar missions with accurate data rather than theoretical estimates. Scientists and engineers who think seriously about interstellar probes, even robotic ones at vastly reduced scale compared to any crewed vehicle, have consistently identified the radiation environment as one of the primary engineering challenges. The Breakthrough Starshot concept proposed by the Breakthrough Initiatives program imagines sending gram-scale probes to Alpha Centauri using laser-driven light sails. Even at this tiny scale, radiation tolerance is a critical design parameter. The galactic cosmic ray flux measured by Voyager provides the baseline against which those tolerances must be designed. Understanding the local interstellar medium also matters for interpreting astronomical observations of other star systems. When astronomers study the astrospheres of other stars, they compare those observations to models of how stellar winds interact with the surrounding medium. Those models are calibrated in part against the in-situ measurements that Voyager provided. The data from 2 small spacecraft drifting through our galactic backyard has improved our ability to interpret observations of stellar environments throughout the galaxy. The 2 Voyager crossings sampled different parts of the heliosphere's asymmetric surface, providing information not just about the interstellar medium itself, but about how the heliopause varies in character depending on where along its surface you cross it. Voyager 1 passed through the upstream nose region heading northward at approximately 122 astronomical units. Voyager 2 exited through the southern flank at approximately 119 astronomical units. The 3 astronomical unit gap between their crossing distances was the first direct evidence from 2 independent measurements that the heliopause varies in distance depending on where you cross it. The differences went beyond geometry. The plasma conditions at the 2 crossing points were not identical. Voyager 2's direct plasma measurements showed a slightly different density and temperature profile compared to what Voyager 1's indirect plasma wave measurements had indicated 6 years earlier at a different location. The magnetic field properties differed as well, with Voyager 2 recording a somewhat sharper magnetic transition. These differences confirmed that the heliopause is not a rigid, uniform surface, but a dynamic boundary between 2 fluid systems shaped by turbulence on both sides, buffeted by coronal mass ejections from within and interstellar pressure variations from without. Between Voyager 1's crossing in 2012 and Voyager 2's crossing in 2018, the Sun had gone through the peak of solar cycle 24 and was descending toward the subsequent solar minimum. The heliosphere's properties had evolved accordingly. Comparing the 2 datasets showed how the boundary adjusts to changing solar wind conditions on timescales of years, providing a dynamic portrait of the heliopause that a single crossing could never have captured. The data from both spacecraft now resides in NASA's archives, published in peer-reviewed journals and available to researchers worldwide. The particle counts are recorded, the magnetic field vectors are stored, the plasma densities are published. Voyager 1 and Voyager 2 have given humanity its first direct measurements of the interstellar medium, and those measurements are now part of the permanent scientific record. What remains unknown, and what future missions will need to address, is how representative the local interstellar medium is of the broader galactic environment. Voyager has sampled one point in space at one point in time, in one particular region of the interstellar medium. The local interstellar cloud through which we are currently passing has specific properties that may differ substantially from other interstellar structures. Denser molecular clouds, which are the birthplaces of new stars, have particle densities orders of magnitude higher than what Voyager has measured. Hot, low-density bubbles created by recent supernova explosions have much lower densities and very different magnetic structures. The interstellar medium is a diverse and variable environment, and Voyager has sampled only one small corner of it. Scientists at NASA and other institutions have discussed concepts for dedicated interstellar medium probes that would build on the Voyager legacy. An interstellar probe mission, studied in various forms over several decades, would be designed specifically to travel far beyond the heliopause, while carrying modern instruments with far greater sensitivity and capability than the equipment aboard the Voyagers. Such a mission would provide a far richer characterization of the local interstellar environment, potentially sampling multiple points along different directions relative to the heliosphere, and carrying instruments designed from the outset to measure the interstellar medium rather than the outer planets. The propulsion requirements for such a mission are challenging but not prohibitive. To reach meaningful distances in the interstellar medium within a reasonable mission timeline, say 100 or more astronomical units within 20 to 30 years, a spacecraft would need to be launched with considerably higher velocity than the Voyagers. Solar gravity assists, using a close perihelion pass near the Sun to extract maximum gravitational energy, have been proposed as one method. Nuclear thermal or nuclear electric propulsion systems could provide higher specific impulse than chemical rockets. The engineering is feasible at a level that has no parallel in the challenges of crewed interstellar travel. The scientific return from such a mission would be substantial. It would allow direct sampling of the heliotail, the region downstream of the heliosphere's motion through the interstellar medium that neither Voyager has yet reached. It would characterize how the heliopause and heliosheath vary across different regions of the boundary. It would sample the interstellar medium at multiple distances and from multiple directions, building a three-dimensional picture of the local environment that the two Voyager measurements cannot provide. In the meantime, the Voyagers continue their drift. Every day they move farther from the Sun. Every day their power output drops by a fraction of a watt, their signals grow a fraction more faint, and the baseline of measured interstellar conditions extends by a few million miles. The data continues to arrive, slowly, patiently, at 160 bits per second from the most remote instruments humanity has ever deployed. When those signals finally stop, the two spacecraft will carry on in silence. They will drift through the local interstellar medium for thousands of years, passing through the outer reaches of neighboring stellar systems, continuing along trajectories set by gravity and engineering in the 1970s. They will become the most distant artifacts of human civilization, moving outward through a galaxy they have helped us understand in ways we could not have anticipated when they were built. The legacy of the Voyager mission is not only scientific, it is philosophical. These two spacecraft, built with technology less powerful than a modern greeting card, designed for a 5-year mission to the outer planets, have provided direct evidence of conditions that define the nature of the galaxy as a habitat. They have confirmed that the space between stars is not a neutral backdrop, but an active, measurable, physically consequential environment that presents formidable challenges to anything that enters it. They have transformed the question of interstellar travel from a question about distance to a question about the nature of the medium that must be crossed. The numbers are on the table, the particle counts are recorded, the magnetic field measurements are archived, the plasma densities are published. What those numbers mean for the future of exploration, for the search for other civilizations, and for our understanding of our place in the galaxy is a question that the data itself cannot answer. That belongs to the people who received it. The biological consequences of long-duration exposure to the full galactic cosmic ray flux deserve closer examination, because they represent one of the most concrete and well-characterized barriers to any crewed interstellar mission. Astronauts aboard the International Space Station, which orbits within Earth's magnetosphere and well inside the heliosphere at an altitude of roughly 400 kilometers, receive a radiation dose approximately 10 times higher than a person at Earth's surface. This comes mostly from trapped radiation in the Van Allen belts and from the fraction of galactic cosmic rays that penetrate both the heliosphere and Earth's magnetic field. Even this modest cosmic ray exposure is carefully tracked and limited. NASA imposes lifetime career dose limits on astronauts, and those limits constrain how long any individual astronaut can spend in low Earth orbit. A crew traveling beyond the heliopause would face the full, unshielded galactic cosmic ray flux. The radiation dose rates in interstellar space, based on Voyager's particle measurements and standard radiation transport models, would substantially exceed the annual limits currently imposed on astronauts by every major space agency. Over a multi-decade interstellar transit, the cumulative dose would be severe. Elevated cancer rates, cardiovascular damage, cataracts, and potential central nervous system effects, including cognitive decline, represent the primary concerns. These are not speculative possibilities. They are direct extrapolations from measured particle fluxes using well-established radiation biology. The biology of heavy ion damage is particularly sobering. High-energy heavy ions, such as iron nuclei, traveling at nearly the speed of light, deposit energy along a narrow, dense track through tissue. Within that track, the ionization density is extremely high, and the resulting DNA damage is qualitatively different from the damage caused by lower energy photons or electrons. Rather than producing isolated single-strand breaks in the DNA double helix that cellular repair mechanisms can readily fix, heavy ions produce clustered lesions, multiple simultaneous breaks and chemical alterations concentrated within a few nanometers. These clustered lesions are far more difficult to repair accurately. Even when cells successfully rejoin broken DNA ends, the accuracy of the repair is lower for clustered damage, increasing the probability of mutations, chromosomal rearrangements, and other alterations that can contribute to cancer or cellular dysfunction decades later. The central nervous system may be particularly vulnerable. Neurons are largely non-dividing cells, meaning they cannot replace themselves after damage the way most tissues can. Studies using particle accelerators to expose rodents to simulated galactic cosmic ray environments have shown behavioral changes, cognitive impairment, and structural alterations in the brain following exposures at doses and rates relevant to long-duration space missions. These results are preliminary, and translating them to humans involves significant uncertainties, but they raise genuine concern about the neurological consequences of multi-decade exposure to the galactic cosmic ray environment that Voyager has measured. The shielding problem does not have a straightforward engineering solution. For conventional passive shielding, adding material reduces the flux of lower energy cosmic rays, but, above certain energies, produces secondary particle cascades inside the shield that can deliver higher doses to the protected interior than the unshielded cosmic rays would have. The optimal thickness of any given shielding material involves a trade-off between primary particle reduction and secondary particle production, and for the hardest component of the galactic cosmic ray spectrum, even the best passive shielding provides limited protection. Water has been proposed as a shielding material for crewed interstellar missions, partly because the hydrogen it contains is effective at moderating the secondary particle production. A spacecraft whose habitable volume is surrounded by a deep shell of water would provide better protection than an equivalent mass of aluminum or polyethylene. The water would also serve as a resource for crew consumption, potentially making the shielding mass do double duty. But the mass required for meaningful protection against the full interstellar cosmic ray spectrum remains formidable, and the power requirements for maintaining habitable temperatures within such a shielded volume, far from any star, add another layer to the engineering challenge. These considerations are not abstract. They represent the physical reality that Voyager's measurements have now quantified. Before Voyager crossed the heliopause, discussions of interstellar travel could invoke uncertainty about what conditions actually prevailed beyond the heliosphere. That uncertainty is now substantially reduced. The particle fluxes are measured. The magnetic field environment is characterized. The plasma density is known. Any future mission planning that ignores these measurements is working from fiction rather than data. The same measurements that constrain crewed interstellar travel also inform the design of robotic probes. Even an uncrewed probe faces the radiation environment. Electronic components can be damaged by energetic particles. Memory cells can be corrupted by single-event upsets. Instances where a cosmic ray deposits enough charge in a memory element to flip its stored bit. In the heliosphere, single-event upsets are a known hazard, and space engineers design around them using radiation-hardened components, redundant systems, and error correction codes. In the interstellar medium, the particle flux is higher, and the duration of exposure for any mission designed to reach the nearest star or beyond is measured in decades or centuries. Error correction codes and redundant systems help, but they cannot eliminate the cumulative statistical probability of component failures over timescales that far exceed any spacecraft's design life. The Voyagers themselves provide a useful data point. They have operated in the near and far reaches of the heliosphere for nearly 50 years, accumulating radiation doses and surviving anomalies that have forced engineers to compensate and adapt. Some instruments have failed, some functions have degraded, but the spacecraft continue to operate. Their longevity is partly a testament to the robustness of 1970s engineering, partly a result of conservative design margins, and partly luck. Extrapolating from their performance to a spacecraft that must operate in the interstellar medium for decades or centuries is a significant leap, but the Voyager experience provides at least a lower bound on what is achievable. The lesson is not that interstellar travel is impossible. The lesson is that the interstellar medium represents a real, measured, quantified engineering environment with specific properties that any interstellar mission must accommodate. The Voyager data defines that environment with unprecedented precision. Every serious engineering study of interstellar probes or crewed missions now has a measured baseline to work from, rather than a theoretical estimate. That is a significant scientific achievement, even if the implications are sobering. There is also the question of what the interstellar medium data tells us about the history of our solar system and the conditions under which life arose on Earth. The heliosphere has not always had its current properties. The Sun was more active when it was younger, producing a stronger and more variable solar wind. The young Sun likely inflated a larger heliosphere than the current one, providing stronger shielding against galactic cosmic rays during the epoch when the first life on Earth was emerging roughly 3.5 billion years ago. As the Sun has aged and its activity has gradually declined, the solar wind has weakened slightly and the heliosphere has evolved. The precise history of heliospheric size and effectiveness over Earth's lifetime is an active area of research, informed both by solar evolutionary models and by observations of young Sun-like stars at different stages of development. The iron-60 isotope deposits in deep-sea sediments offer a different window into the past relationship between our heliosphere and the local interstellar environment. Iron-60 is produced primarily in massive stars and distributed through their surroundings when those stars explode as supernovae. When enhanced concentrations of iron-60 appear in sediment layers, they suggest that supernova debris has passed through the inner solar system, implying that the source supernova occurred within a few hundred light years. The fact that these deposits appear at specific geological horizons, rather than being uniformly distributed through Earth's history, indicates that the solar system has experienced discrete episodes of enhanced interstellar material rather than a continuous uniform exposure. These episodes correspond to times when the local interstellar medium was denser and more turbulent than it is today, when the heliosphere was likely compressed and the cosmic ray shielding was reduced. Correlating these events with the geological and biological record is a developing field. If heliospheric compression events have produced measurable changes in Earth's radiation environment, and if those changes have influenced biological evolution, climate, or atmospheric chemistry, then the history of life on Earth is partly a history of our solar system's journey through the galaxy and the changing protection afforded by the heliosphere along the way. This is the deepest implication of Voyager's measurements. The spacecraft did not just tell us what the interstellar medium is like today. It provided the first in situ data point with which to anchor our understanding of how the local galactic environment interacts with our solar system over time. The numbers Voyager measured are the current values of quantities that have been changing throughout Earth's history and will continue changing into the future. They are a snapshot of an ongoing dynamic relationship between our star, its protective bubble, and the hostile medium of the galaxy. Every number in Voyager's data archive represents the boundary between familiar and unfamiliar. Below those numbers, the conditions that have permitted 4.5 billion years of planetary evolution and 3.5 billion years of biological history. Above those numbers, the conditions that fill the overwhelming majority of the galaxy and that pose challenges to any object that leaves the heliosphere's shelter. The boundary is real, it is measured, it is crossed, and what lies beyond it has now been characterized, particle by particle, field line by field line, frequency by frequency, by the two most distant machines that human civilization has ever built. The data is in, the rest is what we do with it.